I already started with this question, but I had a problem with the record, so I'm redoing it. So let's go again. I just read the question. The following table shows plasma concentration obtained following IV administration of a dose of 250 milligram. That drug shows a characteristic of one compartment model and eliminated exclusively using urinary excretion or through urinary excretion. You have the concentration in microgram per milliliter versus time. Okay, and then the first thing that you need to do once you have your experimental data or your samples, you need to draw what you have. And I mean by drawing, to sketch, either sketching in your mind or just draw it as it's needed exactly. So in here we are showing the data that we have, okay? And then we draw CB versus time on a rectilinear profile, and you can see on this axis, which is y-axis, the profile is showing you that it's a linear profile, okay? You may have it also as CB versus time on a similog graph, and if you see here, the graph is on the y-axis is on a log scale, okay? And we can see that we already have exponential profile that changed visually to be linear, which is one indication that we are talking about linear kinetic. And again, because you don't know anything other than the IV bolus, one compartment, and linear kinetic, now you know nothing other than this profile. But if you already know other models, which we will know through this course, you will know that this will show you visually by knowing that you have a one compartment linear kinetic, okay? But as we know, we can't work on CP as it is versus time on this or on this. We need to either change it to the y-axis to log terms or length terms. So what I did here, I just draw log CB versus time, and we did a linear regression to get this equation, which is the linear regression equation of log CB versus time. Okay, so I may give you the profile and give you the equation with it, or I may give you in the question or show you this as words, just linear regression equation of log CB versus time. And let me just write the equation that we have of linear regression log CB versus time y 422x plus 19705. Okay, so the first thing that you need to do is this, okay? Then if we go back to what is needed in the question, we can find that you need to determine from requirements A to D, you need to determine half-life, elimination half-life, K, CB node, and VD, okay? So let's go and see what you can do by just knowing the equation, okay? So we have, again, this is from log CB versus time, so you can use this and you can use this too, okay? This is what? The slope. So the slope, and this is y-intercept, right? So if the slope equals minus 2422, the slope we know when it's on log term right? So you can determine K, which will be equal to 0.5758 unit or minus 1. From this, you can determine directly your half-life, which is equal 0.693, okay? And as it's our minus 1, then the half-life will be in the unit of hours, okay? So by this, you finished this and this. We need to determine CB naught, okay? We know from the y-intercept, which is equal to 1.9705, that this equal to log CB naught, right? From the equation. Then take the antilog of that to determine CB naught, which will be equal to 93.43. The unit will be the same unit as the concentration, which is microgram per milliliter, right? Because it's in microgram per milliliter as unit. So you are done with this, okay? Let's determine VD if you have a dose of 250. We know that the CB node equals X node over VD. Then we have this, and we need this, okay? If you have this, no, this is what we need, sorry. If you have this as 250 milligram, and you have this 93.43 milligram per milliliter, you can determine this, and you will have VD that is equal to 2.676 liter, okay? And by this, we finished what is the main requirement here from A to D in the question that we have, which is number 4. Okay, let's continue. Using the answers obtained in part A to D to determine the following. The plasma concentration at 75 minutes following the administration of 2.5 milligram per kg to a subject weighing 70 kg. Okay, before going to this, we know under first order kinetic, we have constant parameters, okay, which are K, half-life, elimination half-life, VD, and clearance, okay? Those won't be changing by changing the dose, okay? But other than that, you need to make sure that the dose is changing or not to make sure that you correct for that or not. So the question is telling us that we have or we need to determine the concentration at time equals 75 minutes. So be careful that the time is in the unit of minute. So we need the concentration if the dose administered is equal to 2.5 milligram per kg to patient or individual with a weight of 70 kg. Okay? Notice one thing, that the given dose is changing, okay? So accordingly, the CB node would be different. So first thing, you need to know that the time should be in hour, okay? Because the K that you calculated is in our unit, okay? Also, the time that you have is in our unit. you either change it to hour or you change the K or anything that you are using to the minutes unit if you want to keep it as minutes, okay? Here we need to correct this because it's per kg. So those would be equal to 2.5 milligram per kg multiplied to 70 kg. Okay, this will go with this, and then the dose, new dose. So let's call it prime equal to 175 milligram. Okay, the time when we have again how to change the time to hours. We know that each 60 minutes is 1 hour. What about 75 minutes, right? As simple as that. So you will have the time that is equal to 1.25 hours. Now you can go with the calculation. Easy. CB at time. Oops. At time. Oh, okay. We selected a different icon. The time at 1.25, concentration at time 1.25 equals CB naught E minus K with time. Okay? Then CB naught would be a different CB naught because it's equal X naught, which is the new one, over VD multiplied to the same K, and the time will be 1.25. So this will be 1.25 hour. This is constant and it's not changing, which is equal to 0.5578. Okay. Hour minus 1. This is constant. And this is the new dose, which is 175 milligram. This is constant because we are talking about linear kinetic. And again, be careful if you are using it in unit of liter, okay? Or you just change it to milliliter, okay? And to determine CB naught at this time, CB at 1.25, this will be equal to 3226 milligram per liter, which is 3.226 microgram per milliliter. Okay? And by this, we are done with this part. Okay? The last one, which is the time at which the plasma concentration of the drug will fall below 20 microgram per milliliter following the administration of 275 milligram dose. Again, we are having different dose, so CB naught would be different, so we can't use the same CB naught in the question. And it's asking the question asking about the time for a concentration to fall below certain concentration. So let's sketch the question to understand it. So it's, let's say, CB versus time, and we are on rectilinear profile. This is our profile, right? And then if this is the concentration that we are asking about, which is 20 microgram per milliliter, right? This is the question that is given in the, or the concentration that is given in the question. And then it's asking you about this time. What is the time that the question, the concentration went below that concentration, okay? So it's asking about the time. The only thing that you need to take into consideration that the dose was different. So X naught it's our third different dose, 275 milligram. Okay, so we need to correct for the dose that is given. So your CB node would be different, which is X node 3. Okay, let's call this 3 over VD. This is what? Constant, right? So this would be 275 milligram over, it was 2.67 liter. Then CB node, let's say 3 equals to milligram per liter. Okay, it's, did I finish? No, I need the time. So to reach certain concentration, so CB at that time equals CB node E minus K with time. This equals to 102.996. And again, it's milligram per liter, which is as a unit, microgram per milliliter. So 20 microgram per milliliter, we are using the same unit. And this is constant, which is 0.5578. Okay, and this is the time that we are asking about. Okay, play around with the equation that you have. You'll find that the time is equal to 2.7, no, sorry, 2.93 hours. Okay, and by this we finish question 4, and I will continue in the coming video to start with question 8.